right, so here we go. Unit 9. Let's review. How do we interpret the p-value of a test? So the p-value is when we assume, assuming the null hypothesis is true. Now, obviously, we would write that in context of the problem, but assuming the null hypothesis is true, there is a blank. Now, this is where you would put the actual p-value. There is a blank probability of getting a sample proportion. This is going to be whatever your p-hat is, as extreme or more extreme by chance alone. So that's our p-value interpretation. It's basically once I get my sample, it's the probability that that sample happened by chance, by sampling variability. Okay. There is a problem later on in the review where we do that in context of a problem. So I definitely would recommend that if you're wanting to see how it's interpreted in context of the problem, make sure you look at number 9A as well. Okay, what is a type 1 error? Type 1 error is when we have rejected the null hypothesis but should not have. So we have rejected the null hypothesis, but we should not have. The only time that that can occur is it occurs if the p-value is less than the alpha value, which leads us to a rejection of the null hypothesis. That's the only time it can occur. Okay. A type 2 error let's scroll. A type 2 error is when we fail to reject the null hypothesis, but should have rejected. This can only occur when our p-value is greater than the alpha value, and that leads us to a fail to reject. Now, the probability of a type 1 error is literally just the alpha value in the problem. It is just whatever the alpha value is from the problem. And the probability of a type 2 error is called beta. The power of a test, this is the probability of correctly rejecting the null hypothesis. And also remember that power is equal to 1 minus beta, the probability of a type 2 error. Okay. All right, and then how can we increase power? So to increase power, we can do a couple of different things. The first thing we could do is we can increase our sample size. When we increase our sample size, we have a better representation of our population, a better chance of making a correct decision to reject the null hypothesis. Or we can increase our significance level, which is alpha. So either one of those, I can either increase my sample size or increase my significance level. All right, let's do a couple of examples. So Ms. Lakey believes that less than 75% of students at, hang on, let me get this in the right place here. There we go. Ms. Lakey believes that less than 75% of students at McKinney Boyd High School completed their math homework last night. The math teachers inspect the homework assignments for a random sample of students at the school to help Ms. Lakey test her claim. State the appropriate null and our alternative hypothesis, and be sure to define your parameter. So the null hypothesis and the alternative hypothesis. Now, the suspicion here that I have is that the true proportion is less than 0.75. So what that means is that my null hypothesis would be that it is 0.75. So we always assume that we have an equal to in our null hypothesis. And then P is going to be the true proportion of MBHS students who completed homework last night. And that's all we have to do for this problem. We don't have to do anything else to answer this particular question. All right, number nine. So we've got a roulette wheel. A roulette wheel has 18 red slots out of 38 slots. To test if a particular roulette wheel is fair, you spin the wheel 50 times and the ball lands in the red slot 31 times. The resulting p-value is 0.0384. And so this is interpreting our p-value in context of this problem. So one thing I do want to mention here is if the roulette wheel has 18 out of 38 red slots, then I should expect to get 18 out of 38 red, whatever that proportion is, which is 47%, 0.47. I should expect to get 47% red whenever I play this game. But if you notice, your p hat here is 31 out of 50. I played the game 31 out of 50 times, and what that tells me is that I got a sample proportion of red of 62%. So it looks like there's something off about this roulette wheel. I should have been getting 47% red, but I actually ended up getting 62% red. So something seems a little strange. The probability that this happened by chance alone is 0.0384. And that's what we're going to do now, is we're going to interpret this result in context of the problem. So, assuming the proportion of red slots is 0.47, so that's assuming this null hypothesis would be true, that P is equal to 0.47. Assuming the proportion of red slots is 0.47, there is a 0.0384 probability of getting a sample proportion of 0.62 or greater by chance alone. So there's basically like a 4% chance that this result was this different by just sampling variability, or just by chance or by accident, basically. So that makes us kind of think that there's a little something going on. So are these results statistically significant at the alpha equals 0.05 level? So what conclusion would you make? So if I have a p-value that's 0.0384, that is less than the alpha value of 0.05. That would lead me to reject the null hypothesis. That means that there is convincing evidence that the proportion of red is greater than the 0.47. So what that tells me is that this roulette wheel is not fair. It's not a fair wheel. And that means we have statistically significant results. So are the results statistically significant? Yes, they are. Okay. Because we have rejected the null hypothesis, we have evidence to show that we have a roulette wheel that is probably not fair, then we can say that we have statistically significant results. Now, of course, the casino manager is going to come over and is going to say, now wait just a second here. You're saying that my roulette wheel is not fair. So he makes a 99% confidence interval, and he gets 0.44 and to 0.8. And he says that this interval provides convincing evidence that the wheel is fair because that interval has 0.47 in it. But here's the problem, okay? So 0.47 is in this interval. However, our alpha was equal to 0.05. So a 95% confidence interval should have been used instead of the 99%. Because remember, the 99% is going to be way wider than the 95% confidence interval. So what he has done is he has overcompensated his confidence interval to try to make sure that the 47 is still in there. So we would definitely tell him that he would need to do a 95% confidence interval in order to prove to us that 47 is still in that interval. So we are still suspicious of the wheel. So I would not play roulette on this wheel if you're trying to have a fair game. All right, number 10. Number 10 is our state plan do conclude. So let's go ahead and do that. Okay, a drug company has developed a new vaccine for preventing the flu. The company claims that fewer than 5% of adults who use its vaccine will get the flu. To test this claim, researchers give the vaccine to a random sample of 1,000 adults. Of these, 43 get the flu. Do these data provide convincing evidence to support the company's claim? So we're going to do the full state plan do conclude here, okay? All right, so state. We will test at alpha equals, and we're going to use 0.05 because it was not given to us otherwise. Our null hypothesis is that the true proportion would be 0.05. Now that's because of the 5%. That has nothing to do with the alpha level. That they're just coincidentally are the same. The alternative here is that P is less than 0.05, and P is the true proportion of adults who get flu after the vaccine. So this company thinks that the true proportion is going to be less than 5% because obviously they think that their vaccine is good. All right, now we're going to plan. We've got random. We have an SRS of 1,000 adults. Our 10% condition, 10 times our sample size has to be less than the population. 10 times 1,000 is less than the population of adults, so that one's fine. And then our normal condition, we need to check n times p naught has to be greater than or equal to 10. So 1,000 times 0.05, that's 50. That one's fine. And then we're going to check n times 1 minus p naught has to be greater than or equal to 10. 1,000 times 0.95, that's 950. That is also greater than 10. So we're good to go. Time for do. We're going to use a 1 prop z test in our calculator. Remember, that is under stat test 5. Stat test, and this is number 5, a 1 prop z test. It's asking us, first of all, for P naught. Remember, P naught is your value from your hypotheses. That's 0.05. X is your number of successes. There were 43 that did not get the flu, or that did get the flu, that got the flu after getting vaccine. And then N is our sample size. That's 1,000. And then we have our proportion of success is less than 0.05. So we're doing a proportion is less than 0.05. And then when we do this, we're going to get our z-test statistic and our p-value. So when we get the numbers, our z-test statistic is negative 1.016. And our p-value is 0.155. All right, now we're going to conclude. Since our p-value is 0.155, that is greater than our alpha value of 0.05. Again, that's coincidental that was the same value as our hypothesis. So this means we're going to fail to reject the null hypothesis. And that is because there is not convincing evidence that P is less than 0.05. So that means we have convincing evidence that this vaccine is not actually lessening the amount of flu. So, all right. So be prepared to do a full state plan do conclude on your test tomorrow. Okay. All right, so let's continue with this problem. The next part says, what type of error might we have made, and explain? So since we failed to reject, the null hypothesis, we may have made a type 2 error. All right. From the company's viewpoint, would a type 1 or type 2 error be more serious? So let's discuss the difference here. So a type 1 error, that is when you reject the null, should not have. So what does that mean? That would mean that they say the true proportion is less than 0.05, but it's not. That means that they're going to basically say the vaccine works, but it doesn't. So that is, we say vaccine works, but does not. All right, so type 2, this is when we fail to reject, which this is what we actually did here. We failed to reject, but should have. And so this is not saying P is less than 0.05, but it was. So that would be that we don't say that the vaccine works, but it really does. So we say vaccine does not work, but it really does. From the company's standpoint, which one is worse? So basically, if they say the vaccine works, but it does not, then they're going to still sell their vaccine. People are still going to take it. It's just not going to do anything for the people that are taking the vaccine. Type 2, they say the vaccine does not work, so they're probably not going to produce it anymore, and they're not going to get any money because they're not producing the vaccine, even though it did actually work. So I would say from the company standpoint, a type 2 would actually be worse because they're not making a vaccine that works, so they're not getting revenue that they could have gotten. So that would be my answer for that one. Alrighty, let's continue. Now we're going to move into the multiple choice part of the review. After once again losing a football game to the arch rival, a college's alumni association conducted a survey to see if alumni were in favor of firing the coach. An SRS of 100 alumni from the population of all living alumni was taken, and 64 of the alumni were in favor of firing the coach. Suppose you wish to see if a majority of living alumni are in favor of firing the coach. What would be the appropriate test statistic? So remember, for our test statistic, we have p hat, the value, minus the mean of the distribution, which is the claimed value, divided by the standard deviation of the distribution, which includes the claimed values, p naught. So that's going to be the format of our sample. So p hat, this is our sample proportion. We had 64 out of 100 that said that they supported it. So p hat is 64.64. So that number needs to go first. So I can go ahead and cross out any where that number is not first. The p naught, this is there a majority? Majority is 50%. So the p naught, the claimed value, would be 50%. So anywhere you see a p naught, that's where 50% should go. So you can already go ahead and see that we can cross out A because it's using the 64 on the bottom, and we can cross out D because it's also using the 64 on the bottom. So the answer would be C. We've got our value of p hat minus our claimed value, and then we've got our claimed value on the bottom, 1 minus our claimed value, and then our sample size. And so that would be the one that it would be. Okay. Which of the following 95% confidence intervals would lead us to reject p equals 0.7 in favor of p does not equal 0.7 at a 5% significance level? A includes 0.7. 0.7 is in there, so I would not reject it. B includes 0.7, so I would not reject it. C includes 0.7, so I would not reject it. But D does not include 0.7, so I would reject 0.7 for D. All right, let's look at number 13. All right, a researcher claims to have found a drug that causes people to grow taller. The coach of the basketball team at Brandon University has expressed interest but demands evidence. Over 1,000 Brandon students volunteer to participate in an experiment to test this new drug. 50 of the volunteers are randomly selected. Their heights are measured and they are given the drug. 2 weeks later, their heights are measured again. The power of the test to detect an average increase in height of 1 inch could be increased by what? Basically, this question is asking you, how do you increase power? To increase power, you can do one of two things. You can increase your sample size, or you can increase your significance level of your test, which is alpha. So using only volunteers from the basketball team, that's not going to do anything for power. If I use alpha of 0.01 instead of alpha of 0.05, that's actually decreasing alpha. I would be going to 0.01 from 0.05, so that would be a decrease in alpha. Using alpha of 0.05 instead of alpha of 0.01, that's increasing alpha. Giving the drug to 25 randomly selected students instead of 50, that's decreasing my sample size, so that would not work. Using a two-sided test instead of a one-sided test, that doesn't really matter when we're talking about power. So that would be it. C is it. Experiments on learning in animals sometimes measure how long it takes mice to find their way through a maze. The mean time is 18 seconds for one particular maze. A researcher thinks that a loud noise will cause the mice to complete the maze faster. She measures how long each of the 10 mice takes with the noise as stimulus. The appropriate hypotheses for the significance test are what? So on this one, it looks like we have a null hypothesis that the true mean that it takes them to complete the maze is 18. So I would definitely mark out C because that doesn't have an equal to sign, and I would mark out E because that is using X bar instead of mu, which it should be using the true proportion, or I'm sorry, the true mean. And then to complete the maze faster means that the time, 18 seconds, would go down. So that would be a mean less than 18 would be the alternative. Alrighty. Next on 15. Okay, 15 through 17 use the same stem of the question. So let's look at that. It says here, members of the city council want to know if a majority, again 50% majority, of city residents support a 1% increase in the sales tax to fund road repairs. To investigate the survey, they survey a random sample of 300 city residents and use the results to test the following hypothesis. The null hypothesis is that P equals 50%. The alternative is that P is greater than 50%, so greater than 50% would be a majority. P is the true proportion of all city residents who support the 1% increase in the sales tax to fund road repairs. A type 1 error. So remember, type 1, I reject the null, should not have. Now, when I reject the null hypothesis, it's because I believe I have convincing evidence, but my evidence is not as convincing as it should have been. So rejecting the null means that I have found convincing evidence for a majority of residents. I found convincing evidence of a majority of a residents. Find convincing evidence. Not finding convincing evidence, that automatically crosses out D and E. So I've rejected the null hypothesis because I think I have convincing evidence for a majority, but in reality, I don't have the kind of evidence that I need to have. So in reality, there isn't convincing evidence of a majority. The reason that B is not it, because it says in reality, at most 50%, I'm just trying to get evidence for the alternative. I think I have evidence of a majority, but I actually don't have evidence of a majority. That doesn't mean that I have evidence for anything else. I just don't have the evidence that I thought I had. So it's not that it's at most 50%. It's just that I made a mistake in the evidence I did get. And again, same thing with C. In reality, I can't go and say, well, in reality, I actually have this. I was only trying to collect evidence for one thing, and that was that I have a majority. So my answer here would be A. All right, in number 16, it says in the sample, 158 of the 300 residents support the 1% increase. What is the resulting p-value? So in this problem, I need to get the p-value. I know it's a multiple choice question, and it doesn't require you to do a full state plan do conclude, but you can still use your calculator to get your p-value. So we're going to actually go to stat, test, and this is number 5, the one prop z test. The claimed value is 50%, 0.5. Your sample size, the success in your sample was 158. Your sample size was 300. And our proportion that we are testing is that it is greater than the claimed value. When you plug all of this in, you get a z-test statistic of 0.924, and you get a p-value of 0.1778. And when I look at my answer choices, it looks like my answer is C. That's just the p-value rounded. And again, what is the correct interpretation of this p-value? Again, remember p-value, we interpret it as assuming the null is true. So assuming, remember null hypothesis is that p equals 50%. So assuming that 50% of residents support the tax increase, assuming that more than, nope, that's the alternative. I'm not assuming the alternative, I'm trying to prove the alternative. So, and then these two are just out because they don't even match the format. So assuming that 50% of the residents support the tax increase, there is a p-value probability, okay, that the sample proportion would be as extreme or higher by chance alone. Or there's an 18% chance that the null hypothesis is true. No. We're talking about the probability of getting a sample proportion of what we got. So the answer here would be C. All right, last page, number 18 through 20. Again, we have another set of questions here. Number 18 through 20 refer to, keep losing my mouse. All right, 18 through 20 refer to this setting. A sample survey interviews SRSs of 500 female college students and 550 male college students. Researchers want to determine whether there is a difference in the proportion of male and female college students who worked for pay last summer. In all, 410 of the females and 484 of the males said they worked for pay last summer. Let P sub M and P sub F be the proportion of all college males and females who worked last summer. The hypothesis that we are testing are what? So we're always going to assume that the difference is nothing, that there's no difference. So we can cross out D and E. Now, if I am trying to see if the true proportion of males is different than the true proportion of females, then I would be looking at a difference that is not equal to 0. So that would be A. All right, and number 19. The researchers report that the results were statistically significant at the 1% level. Which of the following is the most appropriate conclusions? If we are told that something is statistically significant at the 1% level, then what that means is we had a p-value that was less than the alpha value of 0.01. We had statistically significant data at 0.01. That means that we rejected the null hypothesis because there is convincing evidence of a difference in the population. In the populations, there's a difference in these populations. So, because the p-value is less than alpha or than 0.1%, fail to reject. Nope. Because the p-value is less than alpha, fail to. Nope. Because the p-value is less than 1%, we're going to reject the null hypothesis. So far, so good on that one. So far, so good on that one and that one. Okay, now, it's because there is convincing evidence that the proportion of all male college students who worked for pay last summer is the same as? No. We've proven that there's a difference. Not that they're the same. We've proven that there's a difference. There is convincing evidence that the proportion of all male college students in the study, nope, we're looking at in the population. Our results are always for the population. There is convincing evidence that the proportion of all male college students who worked for pay last summer is different from the proportion of all female college students who worked for pay last summer. That is our answer. Final question. We have, which of the following is the correct test statistic for a difference in the proportion of male and female college students who worked for pay last summer? So our Z test statistic, p hat 1 minus p hat 2, divided by the square root of p hat 1, 1 minus p hat 1, divided by n1, plus p hat 2, 1 minus p hat 2, divided by n2. We basically just have to find which one of these matches this particular situation. So P hat 1, this would be our proportion of males, because males were first in the problem based on the hypotheses. So the number of males that worked for pay was 484 out of the 550 college students that were surveyed. So that is 0.88. P hat 2 is our females that worked for pay out of our total female sample, which was 500, and that is 0.82. So on the top, I need 0.88 minus 0.82, so I can automatically mark off those two. And then on the bottom, obviously we can see that this one is just for one proportion, so that one's just out. And then we're looking to see which one of these matches. So P hat 1, P hat 2, looks like C is our answer. Good luck on your test.